Calculus section 3.5, equation solving and modeling. This is our day 3. And so we're going to be spending most of our time, we'll talk about some logarithms, but down here with applying Newton's law of cooling and then some extension topics. And again, when we get to the re-expression, we're going to be skipping a couple of these problems because that's just something we've had to cut over the years. So let me get to where we need to be, which is right here. Orders of magnitude and logarithmic models. So orders of magnitude are something that in the Midwest we don't use a whole lot. But it definitely is something that they use to talk about earthquakes. And so out west in California, they would know more about orders of magnitude than we do here in the Midwest. So order of magnitude of a number is the integer portion of the number's common logarithm. So we're talking about log base 10 common logarithm. Two numbers have the same order of magnitude if the integer portion of their common logarithms are the same. So we take the common logarithm and it gives us a number. And what we want to do is compare that to another number. Now, why would somebody do that? Because the numbers involved with things like earthquake, they actually use a unit of measurement, I believe it's called ergs, and they're huge. I mean, they're very huge numbers, so that's why they use logarithm base 10 to talk about them. And order of magnitude is used to make approximate comparisons of like quantities. So it says a kilometer is 3 orders of magnitude longer than a meter. And I think, well, a kilometer is 1,000 meters compared to 1 meter. So the 3 orders of magnitude just comes from the 3 zeros. And that's what it comes from. It's the 3 zeros. Because remember, we're talking about the logarithm base 10. A dollar is 2 orders of magnitude greater than a penny. So if we're thinking in terms of cents, a dollar would be 100 pennies versus 1 penny. And notice, yep, there's 2 zeros. So that's why it's called 2 orders of magnitude. A horse weighing 400 kilograms is 4 orders of magnitude heavier than a mouse weighing 40 grams. So I'm going to write this one in the smallest unit too, which is grams. And there are 1,000 kilograms in a gram. So we're comparing the 40 grams to 400,000 grams, and we notice 4 more zeros. So that's our order of magnitude. New York City with 8 million people is 6 orders of magnitude bigger than Earmuff Junction with a population of 8. Yep, has to have to do with the zeros, because look at that. We went from 8, and then you look at the 8 million, and we have 6 zeros there. So exploration 1 is getting us thinking about why this order of magnitude works the way it does. And it says, using a calculator, compute the logarithm of 4 times 10, then the logarithm of 4 times 10 squared, then the logarithm of 4 times 10 to the third, etc., and figure out what your pattern is going to be. So let's first figure out the logarithm of 4 times 10, which would be the logarithm of 40. Common log, 40. 1.602 to 3 decimal places. All right. Now, I'm not going to use a calculator to see 4 times 10 squared. What I'm going to do is think about the properties of logarithms and how they worked here. So the logarithm of 4 times 10 would have been the logarithm of 4 plus the logarithm of 10, because multiplication in logarithm language is addition. And the logarithm of 10, well, those bases are the same, so they're inverses, and that's actually 1. So the logarithm of 4 must have been the 0.602 piece. Well, let's check that out. Log of 4. Well, there it is. So then I start thinking about the fact that the next one has 10 squared. And I realized that I could write that as the logarithm of 4 times 10 squared, which is the logarithm of 4 plus the logarithm of 10 squared. And that would be the log of 4 plus the logarithm of 100, or you could bring the 2 out in front. But the point is, we know what that is. We know what the logarithm base 10 of 100 is. If you snail shell it, it would be 10 to the something is 100. And that something is 2. And the log of 4, we already know what that is. So notice how, with these two, the difference between them is a 10 when we start. And what it does is it increases from 1.602 to 2.602. And if we continue on, that pattern stays put the whole time. Because 10 to the third power is 1,000. So that is how orders of magnitude work. Every increase of multiplying by 10 puts a bigger integer out in front, because we had 1.602, and then this was 2.602, and this was 3.602, getting a little carried away with my points there. And this would be 4.602. So when we increase by multiplying by 10, what happens is the integer portion, which is the number in front of the decimal, it increases by 1. So for number 2, it says, what is the pattern for those integer pieces? And it is you add 1 for each additional power of 10. 3, what is the pattern of their decimals? Well, the decimal portion is equal. It's that 0.602 each time. They are equal. 4 says, how many orders of magnitude greater is 4 times 10 to the 10th than 4 times 10? Well, this has 10. And 10 to the 10th, we think about the fact that the powers go from 1 to 10. That's an increase of 9. And so that means it's going to be 9 orders of magnitude greater. So when they're talking about earthquakes, we have to remember that each order of magnitude is actually an increase 10 times what it was previously. And that helps people understand why a magnitude 3.4 earthquake and a magnitude 5.6 earthquake is such a big difference, even though they're just, small numbers with some decimals. So orders of magnitude are used to compare, and all of these are logarithmic scales because they're huge numbers. They want to use logarithms to make them something smaller, at least to look at a little bit smaller. Sound or noise, the bell is measured for the order of magnitude in decibels, and its intensity is compared to the threshold of hearing. So the threshold of hearing is the smallest sound that the human ear could hear, which of course is different for each individual person. But in this case, a person that has sound hearing. Severity of earthquakes for the Richter scale, and then something that a lot of people in Minnesota now do in the summertime, acidity of the chemical solutions. And I say that because it seems like every year there's more and more backyard pools. And if you have a backyard pool, you have to make sure that your chemicals are keeping the pH level at the right place so that you don't end up giving everybody hives when they go into your pool. You shouldn't come out really pink. Your pH level should be something that'll make your skin feel pleasant. So example 5 says, let's talk about this earthquake business. Comparing earthquake intensities. How many times more severe was the 2001 earthquake in Jakarta, India, which was a Richter scale of 7.9, than the 1999 earthquake in Athens, Greece, which had a Richter scale of 5.9? And they show us how this is all calculated. So that Richter scale measurement is the log of A over T plus B. Well, before I even go that far, if we know what we're doing, we would say all we'd have to do to compare those two is take 7.9 minus 5.9, and the order of magnitude increase here is 2. But that's the power of 10. So this is 100 times. It was very much more severe earthquake. It was 100 times the original one. But because we don't do earthquakes a whole lot in Minnesota, we're going to do this one the long way. And it tells us that capital R is the magnitude of the earthquake, according to the Richter scale. The lowercase a is amplitude in micrometers of the vertical ground motion at the receiving station. Capital T is period of the seismic wave in seconds. And capital B is weakening of the seismic wave with increasing distance from the epicenter. So when we look at this, we're supposed to say, well, let's talk about the biggest one first. If we want to know the difference between them, we should talk about the larger one, and that was R sub 1. So R sub 1 will equal logarithm of whatever that amplitude was for the first earthquake, so that's going to be A sub 1 over T plus B. Now, we do have to assume that B and T are the same. And that's part of how they're going to measure this, is by the period of the seismic wave. They're going to look at the exact same section of the wave, and that B is something that's been calculated the same distance from the epicenter. And then R sub 2 has a different amplitude. I keep wanting to write the amplitude first. Log of A sub 2 over T plus B. Now we're supposed to compare these two, which means we'd subtract them. So we'd take the logarithm of A sub 1 over T plus B and subtract logarithm of A sub 2 over T plus B. And that should give us the same result as 7.9 minus 5.9. So on the right-hand side, pretty obviously, that's going to be a 2. On the left-hand side, I see that, well, they're both base 10 logarithms. I could condense those two, but I first have to take care of subtracting everything to see what the difference is. So logarithm of A sub 1 over T plus B minus logarithm of A sub 2 over T minus B has to equal 2. And I see that if they use the same B value, the B's are going to cancel out, that weakening of the seismic wave with increasing distance from the epicenter. And in fact, that is one of the things that they try to keep standard. So it would say the logarithm of A sub 1 over T minus the logarithm of A sub 2 over T equals 2. And now we have subtraction, which is, of course, division in logarithm language. And hopefully we would say, well, I'm not leaving that like that, because I know dividing fractions is multiplying by the reciprocal. And we would see that T is going to cancel out, because that's, again, something that they try to keep standard, that period of the seismic wave in seconds. So we'll have the logarithm of A sub 1 over A sub 2 equals 2. Which is fantastic, because A sub 1 divided by A sub 2 is comparing how much greater the earthquake is the second time around. And at this point we have it condensed, so we would snail shell and say 10 squared equals A sub 1 over A sub 2, and 10 squared is 100. Now, it was much faster to do that if we know about orders of magnitude. We can just say 7.9 minus 5.9 equals 2, and that's a power of 10, so 10 squared is 100. But if we don't, then we have to go through it and do it the long way using logarithms, the Minnesotan earthquake way. I do remember when I was a child that the news had said that there was a powerful earthquake on the west coast, and it could be felt in Minnesota at such and such a time. And my parents actually took us outside on the farm in the middle of the yard, and we all tried to feel what the earthquake was. Not a one of us could feel it. It was just too far away, so it wasn't something we were going to be able to go through, which I'm okay with. The ground shaking is not something I really want to experience. All right, in chemistry, the acidity of a water-based solution is measured by the concentration of hydrogen ions in the solution in moles per liter. The hydrogen ion concentration is written as a capital H with a little plus. Because such concentrations usually involve negative powers of 10, negative orders of magnitude are used to compare acidity levels. The measure of acidity used is called the pH. The opposite of the common log of the hydrogen ion concentration, pH equals negative log of capital H plus. More acidic solutions have higher hydrogen ion concentrations and lower pH values. So we're still working on the part of our objective that deals with applying what we know with logarithms. And right away, example 6 says we're going to compare some chemical acidity. Some especially sour vinegar has a pH of 2.4, and a box of Leg-and-Sickle baking soda has a pH of 8.4. Now that's your book trying to be funny, because the sour vinegar part, that's normal. But Leg-and-Sickle baking soda, the most popular baking soda out there is called Arm & Hammer baking soda. Yeah, I know, it's a lame joke, but they tried. You gotta give them that. All right, so we're going to start with the vinegar. And the negative log of H plus, using the formula that they have up there, was 2.4. So we would divide both sides by -1. And then we would snail shell. So we know that common logarithm is logarithm base 10, and it'll say 10 to the negative 2.4. And we would just punch that in on the calculator. So 0.00398, blah, blah, blah. Now, because I do want to see a little bit of this without the zeros in there, we're going to use a little scientific notation. And let's do this. So with scientific notation, we're going to stop right after the 3. If I can get this to go in the right spot. There we go. And we'll go ahead and make it 3 decimals, but after we've done that. So we'll write it as 3.981 times 10 to the negative. And then we actually would be moving the decimal place 3 positions for that one. So we're taking some of those zeros out of the picture. Smartboard is being so ornery today. There we go. In order that we can keep some of the numbers that are really going to matter here, the significant digits of the 398101717. So there's our vinegar. And that's one of the rare times that we use an X to signify multiplication. Not a particular fan of it, but that's what they do in the science area, so that's what we keep. Better with parentheses, of course, because we know that X stands for a variable in math. But in science, they often use that X for scientific notation. And the Leg-and-Sickle baking soda, so I'm just going to put baking soda. That negative log of H plus equals 8.4. So same thing, to solve it, we would divide both sides by a -1. And snail shell, because we know it's common log. So that will be 10 to the negative 8.4. That gives us H plus for the baking soda. So let's take a look at that. 10 to the negative 8.4. Now, isn't that interesting? That one already came up with a scientific notation, but the interesting part is the decimal is exactly the same as what we saw up above, with a little rounding there at the end. So this will be 3.981 times 10 to the negative 9th. And now hopefully you see why I put the other one into scientific notation, because in B, it says how many times greater is the hydrogen ion concentration of the vinegar than of the baking soda. So, comparing those two, we would have the 3.981 times 10 to the negative 3rd divided by 3.981 times 10 to the negative 9th. And if we divided 3.981, it's going to cancel out with 3.981. So we really just need to figure out what do you get if you take 10 to the negative 3rd and you divide it by 10 to the negative 9th. And division, when you have similar bases, is going to be subtraction. So it'll be negative 3 minus a negative 9, which will be negative 3 plus 9, which is 10 to the 6th. And there it is. So it's those powers of 10. It would be 10 to the 6th. And then C says, by how many orders of magnitude do the concentrations differ? And so what we want to do is explain what we found here. They told us orders of magnitude is going to be how many powers of 10. And we just said that that is 6. So the hydrogen ion concentration of the vinegar is 6 orders of magnitude greater than the Legensickle baking soda. And that it's truly the difference of their pH values. I suppose I could write that down too. This is the difference in their pH values. Because that's what we're getting when we are measuring those hydrogen ion concentrations, the measure of acidity. So we've already gone through an example here that was talking about using the Richter scale, seeing how logarithms would come into play because of all the zeros. Then we went through the acidity, the pH, and now here's the big one that was a chunk of our objective, and that's Newton's law of cooling. And Newton's law of cooling is a great thing to have for math parties, because math parties can sometimes, not a lot, but can sometimes have some quiet moments. And when they have quiet moments, you'd want to have everybody grab their calculator and do some calculating. So, an object that has been heated will cool to the temperature of the medium in which it is placed, such as the surrounding air or water. So you've done a lot of cooking, you leave it on the stove, you forget about it. It'll take some time, but the temperature will eventually get to room temperature. And the temperature, capital T, of the object at a time lowercase t can be modeled by there's our fabulous Newton's law of cooling formula. So T of T equals T sub m plus the initial temperature, the null temperature, minus T sub m, times e to the negative kt for an appropriate value k. And k, there is an actual resource out there, whether or not it's on the internet or in a book somewhere, that gives you the values of K, and that comes from the viscosity of whatever it is that you're working with, so how thick it is. And T sub m is the temperature of the surrounding medium. So what's the temperature in the room? And T sub naught, or the null temperature, is the initial temperature of the object. This model assumes that the surrounding medium, although taking heat from the object, essentially maintains a constant temperature. So whatever it is that you made is not so large that it is heating up the whole room, and that way it'll cool down to that room temperature. So now example 7 says applying Newton's law of cooling. And you've got everybody over for a breakfast math party, and you have a hard-boiled egg at a temperature of 96 degrees, and it's placed in 16 degrees water to cool, and this is all in Celsius. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So you have somebody at your math party that says, I never eat my hard-boiled eggs until they are exactly 20 degrees Celsius. Well, you know what that's going to do. Everybody at the math party is going to say, let's calculate it. How long will it take for that to be 20 degrees? The one issue is going to be that we don't want to cheat and look up the K value on Google. So we are going to go ahead and put in all of the variables that are needed here and figure out what K is so that we can then use this to figure out when the egg will be 20 degrees Celsius. All right, capital T of T, that is that ending temperature, and it was at 45 after they had gone through this for a while. And the temperature of the medium, they put it in water, and that water was 16 degrees. T sub naught, or T sub null, is the initial temperature, and that was 96. We can see that when we read the problem. It was at a temperature of 96 degrees. And then we have e to the negative k, which is what we're trying to find. And the time they told us was 4 minutes. All right, so let's simplify this a little bit. 45 equals 16 plus 80 e to the negative 4k. Well, we would obviously subtract 16 from both sides, so 45 minus 16 is 29. And then we would divide both sides by 80. And then we'd take the natural log. And finally, we divide by negative 4. And that would give us the K value. So somebody would grab their calculator and they'd punch that in for us. And to 3 decimal places, our K value is 0.254. So now we're going to use the same formula, but we're going to use it differently, because what we want to know this time is use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So now we want to know, when is it 20? And as we go back through this again, we realize, well, the rest of this is going to be the same, except for this time I know what K is and I don't know what T is. So 16 plus 80 e to the negative 0.254 T. So the 20 changed. The rest of it stayed the same. You still have that 16 degree water to cool, and we still have the temperature of 96 to start with. So we would subtract 16 from both sides and divide by 80, little reducing, so that we'd get 1/20th, and then we'd take the natural logarithm of both sides because the natural log of e is going to wipe that right out for us because they're inverses. And we'll divide by negative 0.254. And after we punch all of that in, we will know that it will be 11.809 minutes. Now, of course, somebody started a timer when you started all of this and says, well, that's great, but I'd really like to know this in seconds. I want to know when this is going to be exactly 20 degrees. So they could take the decimal portion, the 0.809 times 60, and get this as 11 minutes and 49 seconds. So yes, that is a true math party right there. Math parties always have cake and Kool-Aid, and then, you know, something to eat that's more substantial, and that's what we had here. We had the hard-boiled eggs. So there it is. Now, that is our objective right there, using that Newton's law of cooling to figure out the amount of time it's going to take for something to cool off. The extension down here using Newton's law of cooling, that's something we've had to give up for a couple of years because of time. So is the logarithmic re-expression. But I'm going to talk a little bit about that on the next example, which is example 9. So selecting a regression model is what we're looking at here. And it said, decide whether these data can be best modeled by logarithmic, exponential, or power regression, and find the appropriate regression model. So the first thing you would do is make a scatter plot of the data. Now, looking at these data points, hopefully once we do that, we think, well, that's exponential growth. I should use exponential growth. But we would try a couple of other ones to see, you know, how good a fit are they. So this one that's to the left down here, this they use natural log for. And yes, that is kind of, without this arrow here, that does look like what we know of as natural log. And when they re-expressed the data with natural log, it looked like this. Now, these numbers that we had in the table are not incredibly huge numbers. They don't have a lot of zeros in them or anything like that. But you would try it thinking, hey, it's getting a little bit closer here. So the first one, they only expressed the y's in terms of natural log. And in the second one, they did both x and y. Now, what were they hoping for? They were hoping for a straight line. They were hoping that everything would line up perfectly. And if you do the natural log regression on your calculator, which I'm not going to have you waste your time on, if we did that regression, the R value comes out to 0.89255679995. So that does say, you know, there's a little bit of room of error here. You know, we really want that to be as close to 1 as we possibly can. So then we'd try, because like I said, it does look like exponential growth, so we would actually do power regression to see what we get. And I did go ahead and put these in previously. So there they are. Stats, calculate. There's our power regression right there. Enter. Oh, and it's list 1 and list 2. I don't think I want to store it. I'll just show you this. So there it is. Now look at the R value for that one. That's much, much better. That's a much better fit. So our R value for this one came out to 0.996171549.3. So much better. And when you write it out, it would be y equals 1.446 times 1.781 to the x power. And let me pop that back up there so you can see it. So it gives you the model. The very top is the model. Y equals A times X to the B. It tells you what A is, it tells you what B is, and then it gives us our R value. And that's a really good R value that we're looking at there. So power regression would definitely be the best. Now, if you do exponential regression, which again, you might think, hey, I should use exponential because I'm talking about exponents here. It's actually 0.985. So it's not quite as good. The power regression model gives you a better regression than exponential regression. So this particular problem, while not necessarily a part of our objective, I think is really good for you to see, hey, we have to try and see the data and say, what do I recognize this as? And what should I use for the regression? You know, that's part of our job is looking at the math and saying this would be the best thing for me to do. So that takes care of section 3.5. We had an objective there to finish up on. So you'll be doing the bottom assignment here, section 3.5, day 3, 45, 49, 50, 61, and 63. But like I said, I want to get just a little bit of section 3.6 done here to make sure that we're going to have enough time to take care of everything that we have to do. So I'm going to pause this for a second, and then I'm going to pull up the 3.6 notes. Now, 3.6, lots of objectives, and this is all about the mathematics of finance, because you have to be an educated consumer. You know, you want to know what interest should I be getting here. Compute interest on investments, compounded annually, compounded K times per year, compounded continuously. And that brings me to, my daughter just opened up a bank statement a couple of days ago from the credit union. And the credit union had changed hands within the last year. They had a new company that bought them out. And she noticed that her savings account actually had amounts being subtracted from it. And they had a little disclaimer that said that for whatever reason they had changed the minimum balance that you had to have, and she had not met the minimum balance, and so they were charging her to hold her money for her. And I said, you definitely need to get on the phone and say, okay, this is not all right, and this is a savings account, and savings accounts are supposed to earn interest. So if I don't have enough money in there, I'm going to take my money out. I'm not going to give you money every quarter to hold my savings account. And you have to check those things. You have to be careful when all of those mailers come in the mail and they're letting you know about changes in policies. So computing that interest, we've got computed annually, computed K times per year, compounded continuously, and we want to be able to find the APY, annual percentage yield, to determine the better investment, you know, where you should put your money. Calculate the future value of annuities, find the monthly payment to accumulate a future value, find the term of the investment, knowing the monthly payment and future value, and finally, because hopefully, you know, everybody wants to own a home at some point, you have to know about all that good stuff. So calculate the present value of loans and mortgages and determine monthly payment knowing present values. So the mathematics of finance, definitely the science of letting your money work for you. And in case of anything like bonds, savings accounts, all of those things, you're trying to save money for the future. So in the mathematics of finance, we have certain variables that get used again and again and again. And right now, interest rates are incredibly low. Now that's great if you owe somebody money, but it's not so great if you are trying to save some money in savings accounts. And so you really have to think about the amount of money that you're able to put away. The more money that you put away, the more likely you are to get a better return on your investment. So interest is the cost we pay when we borrow money. That's most of us. Most of us are not independently wealthy. Interest is the benefit we receive by making investments or by putting money into savings. And like I said, that's the part that you count on. You put your money in a savings account so that you can earn a little bit of money. Now, the letters that are used a lot when we talk about finance, capital A is the amount accumulated. How much did you have at the end of the year? Capital P is principal. Principal is how much money did you put in to start. Lowercase r is the interest rate, and that needs to be as a decimal. And then N is the number of years or number of time periods. So we've got a little table here that shows interest compounded annually. And this actually is something that we looked at back in Algebra 2. And what it's showing is the formula for simple interest. Simple interest is interest that is compounded only once a year. Now, that's not something that's going to happen at most banks. Usually they're compounding interest quarterly, so every 3 months. So this is the constant percentage growth pattern that you see each year. The value of an investment is an exponential function of time. The longer you leave it in there, the better. Compound interest is interest that's earned on the interest. So that's why it's nice that they're compounding it quarterly. At the end of the quarter, they tell you what you have, and then you earn interest on the interest. Now, interest compounded annually is where we start, because that is a really, really basic formula. So if a principal P is invested at a fixed annual interest rate R, calculated at the end of each year, then the value of the investment after n years is A equals P times 1 plus R to the n, where R is, of course, expressed as a decimal. So number 1, we just have a very basic compounding annual problem. Suppose Quan Lee invests $500 at 7% interest compounded annually. Find the value of her investment 10 years later. So once they say annually, that's once a year. So that means we can go ahead and use our simple interest formula. So we want to know how much money, that's A, if she started with $500 at 1 plus 0.07 is 7% compounded annually, and we want to find the value of that 10 years later. Now, of course, we would do that little bit of addition ourselves, and then we'd punch it in. And this is going to be in dollars and cents, so we're not going to use our 3 decimal places, for goodness sake. We know this is money. So $983, and rounding will do 58 cents. Now, we are rounding like normal. You need to know that banks don't do that. Banks would literally, if you were to take your money out right then and there after the 10 years, you would only get $983.57. And that's because that extra penny is theirs, and they don't want to give it to you until you've reached the next penny. The other thing that you can't do is you can't come halfway through a year and expect to earn that money. Most contracts with banks are fulfilled only if you see an entire year pass. And so you can't put your money in for 3 months and then come in and say, where's my interest? I want all my money out. They're going to say, you don't accrue that interest until the end of the year. But like I said, we'll round it up. Usually cute little kids can get them to round up. If little kids come in with their mom and dad and say, here, we figured out exactly how much money we should have, then yeah, they're going to give it to them, because they could be a customer that'll come back for years and years and years. Now, that is the only piece that I wanted to make sure that I had done with you today, so that I believe we'll be able to finish the rest of this in 2 days. And you have a great 3-day weekend. Enjoy your Martin Luther King holiday. I should be writing a test for you on Monday. But there we are. So have yourself a good weekend. And again, just in case somebody's looking for it, There was the 3-5 day 3 assignment. No new assignment for 3-6.